We've heard a lot about the move structure now, and we know that the move structure is useful for executing permutations. And we motivated all of this with one permutation in particular, which is the LF mapping. But we don't have to be limited to thinking of only that one permutation. So let's just take one more video to remind ourselves what are some of the other permutations we might also be interested in using a move structure to execute. So in our original motivation, we recalled that when we apply the Burrows-Wheeler transform to a repetitive input, we of course get a runny Burrows-Wheeler transform, right? We get long equal letter runs in the Burrows-Wheeler transform. And that this carries through to the LF mapping in the sense that when the LF mapping takes any of the letters in a given run to their destination, it takes them all in parallel. Right, and so we're used to seeing these parallelograms sort of showing how an entire block of letters from the PWT, when it moves through the LF mapping, they move together and in parallel. Okay, right, and here's the picture we saw before of all the parallelograms. So let me just shift to a different example. This one is a little bit easier to fit on a slide, and as you'll see, I also want to fit sort of the text version of this on slides later as well. But anyway, this is another example. It's another sort of runny input. It's kind of like three strings concatenated together with dollar signs between them and then a hash mark at the end. And I've just shown you here the Burrows-Wheeler matrix with the first and last columns highlighted, right? First column here, last column here. But then also to the side, I've got the LF mapping. So in other words, for each of these letters, which is the row that that letter maps to through the LF mapping. So let's just pick as one example, this A here. Okay, looking down the L column, that's the second A, right? So we know it should map to the second A in the F column. That's this A right here. That's at offset 5, so we have a 5 here, okay? So that 5 is just saying the A of rank 1 is at row 5 in the first column of the Burrows-Wheeler matrix. So it's just the usual LF mapping that we're used to. I've also got the FL mapping, right? And I've actually shown that over here. In other words, if we want to kind of do the opposite, if we're at a particular letter in the F column and we want to find which is the corresponding letter of that rank in the L column, then the FL mapping is what does this. It sort of is the inverse of the LF mapping, right? If the LF mapping is about moving to the left by 1 with respect to the text, the FL mapping is moving to the right by 1. And I've shown them both here, and we can of course connect them both by parallelograms. Here I'm only showing the parallelograms for the blocks, right? So there are some individual entries for which I did not draw a parallelogram, but you know, I could have drawn a lot of little ones too, but I thought it would be simpler to just draw the big ones. Okay, so we know that these parallelograms can sort of describe the block permutation that takes us through the LF mapping. And of course, we know that in the formulation of the move structure, we thought about the p bit vector and the q bit vector, the p being the sort of source of the permutation. We're going to permute from the side that's marked with the p bit vector. Q is like the destination. That's the side that we map to when we map through the permutation. Okay, so if this is our p and this is our q, then of course we can build a move structure. Maybe we do some splitting, right? We might need to do some splitting to guarantee constant time queries with our desired bound. Let's just forget that for a moment. Let's just say that we're using this P and Q, and we can build a move structure, and that move structure lets us do pi, the permutation pi, sort of dictated by these parallelograms. And in this case, that's the LF mapping, because we assigned P to the L column and Q to the F column. So when we move through the permutation, we're moving from L to F. Okay, but, and maybe you see this coming, we don't have to do this, right? We could have assigned P and Q the opposite way. We could have let the F column be the P bit vector and the Q and the L column be the Q bit vector, right? So here it is just with P and Q swapped. It actually didn't change the bit vectors themselves, right? Because the parallelograms are the same. Right, so the bit vectors didn't change. I just changed which one I called P and which one I called Q. And so if I build a move structure out of these bit vectors, I'll get the permutation the other way. So whereas my original choice of P and Q meant that when I built the move structure, I was going to get the permutation to be LF, now that I've inverted the sense of P and Q, when I build the move structure, the permutation will be FL. So it'll be the opposite. So let me be clear, this is a different move structure, right? So the move structure that we would have built for the LF mapping, and this move structure that I'm describing here, which is for the other direction, the FL mapping, if you will, those would be separate structures, right? You can't use the same structure for both, right? This one structure only goes in one direction. So we would actually be building two separate move structures. If we wanted both, we could build two separate move structures. They don't use the same table, they're different tables. Furthermore, if we need to do splitting, the splitting might be different, right? In other words, remember the splitting was kind of not a symmetric notion either because we cared about the Q weights and we split in such a way as to reduce the Q weights. Well, if we change which bit vector is P and which bit vector is Q, you can imagine that also leads to different splitting decisions. So these would be separate move tables. They would be subject potentially to different splitting decisions so as to get the constant time queries under our desired bound. But you could do it, right? You could do it either way. It's really just a matter of how do you assign P and Q. Okay, and I didn't say this, it's on the slide, but the FL mapping is sometimes denoted with the symbol psi. Okay, recall this diagram that we looked at before because I just want to remind you, we just talked about LF and FL. We said when we looked at the fundamental movements, we looked at a diagram like this, where on the right we have lex space. So this is the space where everything is in alphabetical order by right context, or you can think of this as this is the Burroughs-Wheeler matrix, basically. And then on the left side we have T space, so that's the original order, right? That's the original text that we got in the original order. Okay, and we said, and the movements between text space and lex space are according to the suffix array and the inverse suffix array, right? So the suffix array is what takes us from ranks in lex space to offsets in T space. The inverse suffix array goes the other way. We go from offsets in T space to ranks in lex space. Okay, and we said the LF mapping was a bit like something that causes us to make large unpredictable movements in lex space, but very predictable movements in T space, because essentially an LF step is moving one step to the left with respect to T. So those three steps labeled 1, 2, and 3, which look like big steps over here going to sort of like arbitrary new places on the Burroughs-Wheeler transform, well, they're predictable because they're always leftward movements with respect to T. So each of these is just a move to the left by 1, or in this picture I've arranged T vertically, so a movement up by 1. Okay, and that's what this expression down here is reinforcing. Now we did talk about another kind of movement, almost kind of like the mirror image of this, where instead of making large unpredictable movements in lex space, but those corresponding to leftward movements by 1 in T space, we can do large unpredictable movements in T space, but movements that are to the left by 1 in lex space. In other words, we can hop around from letter to letter in the original text T according to the lexicographical ranks of the right contexts of those letters, right? And so that's another function. It's different from the LF mapping, right? Because again, it's sort of like we're in mirror image world where the predictable movements are now lex space movements, and the potentially large movements, the movements where we might be hopping all around the text, those are in text space. Okay, and this function that does this we call phi, or phi, right? That's the Greek letter, phi. And likewise, we can have inverse phi. Inverse phi is just like this, except for that it's making rightward movements in lex space. It's moving to the right by 1. Okay, so the last point I want to make about what permutations can we use the move structure to represent is that we don't have to limit ourselves to LF and FL. We can think about phi and phi inverse. So let's just bring back, this is again sort of like the two panels of that fundamental movement slide. I just kind of arranged them differently. This time I arranged T horizontally, and then I arranged the Burroughs-Wheeler matrix the usual way. But it's a bit like the diagram I showed earlier about the fundamental movements. And if we look at the t space part of the diagram, right, we can see here's t itself, here are the offsets with respect to t, and then here's that function called phi. So this is for every letter in t, this is saying, phi is saying, this is the offset of the next alphabetically smaller part of t, okay? So like, for example, this c here, which has gt dollar after it, has a 5 here in the phi function because the c at offset 5 over here is the one that's alphabetically just prior, CAT dollar before CGT dollar. And CAT dollar G comes before CAT dollar hash, so this one is alphabetically later than this one, but it's alphabetically just before this one, right? So we have a 5 here. But that's the idea, right? The phi function is take me to the offset that is lexicographically one less than my current offset. All right, and then inverse phi would go the other way. Okay? So this function, like LF and FL, has long stretches of elements that go up by 1. Right? This is another indication that phi, a lot like LF or FL, is like a block permutation, right? It's taking entire blocks to entire other blocks. And in fact, I can just start drawing the blocks on this diagram. I'm only going to draw the blocks for the consecutive stretches of more than one element that map to the other. I could have drawn in a lot of little parallelograms for the remaining elements, but I didn't do that. But you can see this also has a block structure, right? In total, this will have, I guess, counting both the parallelograms I did and the ones I did not draw, there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of them in this diagram. Okay? So the phi function and the inverse phi function, which again, if we wanted to apply the move structure to execute the phi function, we could do it. The phi function is a runny permutation. Its inverse is also a runny permutation. So if we wanted to represent the phi inverse function, we could. And so the permutation that we represent with the move structure could be any of a variety of permutations that we sometimes use in pattern matching with compressed full text indexes. It's usually the LF mapping. That's the most common of all the permutations that we use in practice when we're using these indexes. Sometimes, though, it's useful to go the other way and do the FL mapping. Likewise, sometimes it's useful to use the Phi and Phi-inverse functions. Examples would be algorithms for computing longest common prefixes, or LCPs, either in lex order or in their permuted text order. Those often use phi and or phi inverse, and can also use LF. Right, so all of these permutations are going to serve some function in some algorithms that we use, perhaps for constructing indexes or perhaps for querying those indexes. This was all observed in the original paper by Nishimoto and Tabe, which talked about building move structures both for LFFL type things, but then also for Phi inverse type things, and it's been sort of observed later as well in later work that uses compressed indexes in more ways. Furthermore, and we shouldn't forget this either, right? The move structure is not only for these compressed full text indexes, it's just for any runny permutation. So there could be other applications that have nothing to do with genomics, but nonetheless involve these runny permutations where, again, the move structure can bring its unique advantages, constant time permutation queries, big O of R, space usage, where R is the number of blocks, the number of BWT runs, or otherwise the number of blocks in the permutation.